Welcome back. As promised at the end of Part 2, we are now stepping away from theoretical methodologies to look at a practical, real-world case study. In this section, we will introduce a reactor vessel system. Our goal here is to define our system boundaries and identify the specific hazards we want to capture, setting the stage before we begin our actual modeling. Let's introduce our case study, a pressurized reactor vessel. We selected this specific system because it perfectly illustrates why advanced risk assessment methodologies are necessary. A reactor doesn't just have one fail-safe. It relies on multiple layers of protection. You have electronic safeguards, like automated shutoff valves, mechanical safeguards, like pressure relief valves, and human protection through operator intervention. Modeling how these diverse, overlapping layers interact and how they might fail together is what makes this the ideal case study. Here is the system diagram for our reactor vessel. During normal operation, the primary cooling loop maintains a stable environment. However, for our risk assessment, we need to focus on the labeled safeguards. Looking at the diagram, you'll see our defense in depth. First, the automated electronic valves, EV1 and EV2, which are triggered by our temperature sensor TS1 and pressure sensor PS1. Next, we have manual valves MV1 and MV2, which can be controlled by the operator, marked as OP. Finally, our last layer of passive mechanical protection is the pressure relief valve, labeled NRV. Let's move to the next slide to see exactly how these layers sequence together to protect the system during a runway reaction, and how they can systematically fail. Let's walk through a runway reaction scenario. When temperature and pressure spike, the initial goal is to isolate the vessel by closing the input valves. Our first line of defense is automated. Sensors TS1 and PS1 detect the anomaly and signal the electronic valves, EV1 and EV2, to close. If they succeed, the system is safely isolated. But what if those electronic valves fail to close? The dangerous inputs continue. Now, our operator, OP, must intervene and manually close MV1 or MV2. If the operator doesn't react in time, or the manual valves are jammed, our isolation layers are completely lost and pressure will build rapidly. This is where our final, passive mechanical layer takes over. The pressure relief valve, the NRV, is designed to be forced open by extreme pressure, venting the system into the atmosphere. While this causes undesirable pollution, it prevents a catastrophic vessel explosion. As you can see, the final outcome depends entirely on how these individual failures interact. A total catastrophe requires multiple overlapping failures, while other combinations lead to intermediate consequences. To evaluate all of these different scenarios, we will apply the deductive and inductive modeling methodologies starting in Part 4. Before we dive into building our actual models in the upcoming sections, let's zoom out and review the general procedure for conducting a formal, rigorous risk assessment. No matter what system you are analyzing, following this standardized framework is critical. Step 1 is to identify the objective of the assessment. Are you looking for a root cause study of a specific system failure? Or are you trying to identify the various scenarios that follow a certain component failure? In the first case, deductive methods should be selected. In the second case, inductive methods should be used. Depending on the method selected, you will define your starting point, either an initiator when an inductive method is used or a top event when a deductive method is selected. The next step is to identify the analysis scope, meaning what failures do you want to include? In some cases, analysts will skip certain types of failures if their probability is extremely low, helping to reduce the complexity of the modeling. Once the scope is set, we define the resolution. This identifies the layer of detail we want to cover. For instance, do we want to stop at the control board level and treat it as one single failure? Or do we want to drill down to the component level, such as individual capacitors? This resolution selection normally depends on the failure data you actually have available. Next, we define the ground rules. This part is very important, especially when the analysis is done within a large group. You want to define how events should be named and how failure models are shared across different teams, making collaboration much easier. Once everything is ready, we can start building the model to map out exactly how the system may fail. During this step, we also quantify the model by assigning specific failure rates, test intervals, and probabilities to our individual base components. The next step is to evaluate the model. We analyze the completed logic to calculate the overall system unavailability, identify the critical cut sets, and calculate the importance measures for individual events. The final step is to interpret the results. We use the analysis to help the management team decide exactly where to invest engineering resources for the biggest safety improvements. This procedure is the backbone of any risk assessment analysis. Now that we understand the general procedure, let's apply those first crucial steps to our reactor vessel. On this final slide, we are defining the exact scope, resolution, and ground rules for the models we are about to build. For our analysis scope, we are focusing strictly on the failure of our safeguards during a runway reaction. This means we are including the automated sensors, the electronic and manual valves, the operator, and the mechanical relief valve, while excluding the primary cooling loop itself. For our resolution, we will model down to the major component level. We will treat a valve failure or a sensor fault as our base events, rather than drilling down into deeper subcomponents like individual wiring or circuit boards. The table on this screen lists the specific events and exact failure modes that align with our chosen resolution. Regarding ground rules, such as event naming conventions, these are typically highly organization-specific. For our tutorial, we will use a general, straightforward naming convention like EV1, EV2, and NRV. Establishing these rules up front ensures our logic remains organized and consistent, especially if multiple teams are collaborating. With our system defined, our scope locked in, and our event table ready, we have successfully completed the first phase of our risk assessment. In Part 4, we will take these exact events and start building our models. I'll see you there.